Hello, welcome to another module in this massive open online course. So, we are looking at M-ary QAM, that is M-ary quadrature amplitude modulation, and we are about to start our discussion on the receiver and receive processing and the bit error rate for M-ary QAM. But before we do that, yesterday we derived the value of amplitude A, right. So, let me just correct this. The amplitude A is square root. Before we proceed further, I am just correcting this, I was missing a square root. So, this is simply square root of 3 ES by 2m minus 1. Okay. So, that is fairly obvious. Let us now start with the receiver. Of course, again we have seen this many times before. The receiver for M-ary QAM, and in M-ary QAM, remember the transmitted waveform x t equals A1 P2 t plus A2 P2 t plus NT, which is the noise. Now, similar to QPSK, we match filter it. Similar to QPSK, we separately match filter matched filter with, well, H1t equals P1 t minus t and H2 t equals P2 t minus. So, you separately for the detection of A1, alright, at the receiver, of course, we are using match filter, the match filter to process the received signal, but we have to remember there are two independently modulated signals, that is A1 on the in phase pulse, A2 on the quadrature, alright. So, therefore, we have to separately match filter xt, once with filter match to P1 t, that is H1 t equals P1 capital T minus t, and once with the filter match to P2, the pulse shape P2 t, which is also, which by the way is orthogonal to P1 t. So, H2 t equals P2 capital T minus t. So, you have two separate match filtering operations, similar to, again nothing different, similar to what you have seen in quadrature phase shift key. Okay. So, since P1 P1 t is orthogonal to P2 t, therefore, when you match filter with H1 t, that extracts the symbol A1 and the component with respect to P2, that is the component symbol A2, the contribution will be 0. Similarly, when you matched filter with respect to H2 t, which is matched to P2, that is P2 capital T minus t, the contribution of A1 becomes 0, because again P1 is orthogonal to P2. Okay. So, this is all these points we had seen in our discussion for QPSK, that is quadrature phase shift key. Okay. So, therefore, what we have here is basically xt, you separately matched filter with H1 t equals P1 t minus t, that gives A1 EP plus N1 tilde, okay, and EP is equal to 1. So, this is simply A1 plus N1 tilde. Okay. Now, notice that in this contribution from A2 is 0. When you match filter with respect to H1 T H1 t minus t, contribution of A2 is 0, since P2 t is orthogonal to P1t. Similarly, here when you match filter with H2t equals P2t minus t, you get A2 EP plus N2 tilde, this is A2 plus N2 tilde. Of course, this is because the energy of the pulse EP is normalized to 1. Okay. And again here contribution of, now here contribution for the same reason, contribution of for same reason A2 is 0, same reason in the sense that P1t is orthogonal to P2t. Okay. And further, if N2 Nt, okay, let us assume that the received signal, this received signal is I am sorry, this is not the transmit, this is Yt, which is Xt plus Nt. Remember Yt is, we are assuming an AWGN channel. We can look at other channels also, but we have restricted ourselves to the simplest and most general case of an AWGN channel so far. So, Nt is additive white Gaussian noise with Nt is AWGN with autocorrelation Rn and tau equals n naught by 2 delta tau, and the mean equal to 0. Then N1 tilde and N2 tilde, these are, we have seen, both Gaussian mean equal to 0 and variance equals n naught by 2 EP, again EP equals 1. So, this is n naught by 2. So, variance, so n naught, so N1 tilde these are Gaussian, mean equal to 0, variance equals n naught by 2. Now, therefore, and further, now this we can call this as A1 plus N1 tilde, we can call this statistic as R1t, that is followed match filtering and followed by sampling at t equal to capital T. This we can call this as R2t. Now, the decision rule for each R1t, now what is the decision rule? Decision rule that is decide A1 from R2t and decide A2 from A1 from R1t, A2 from R2t, and remember these are PAM symbols. So, decision rule is similar to PAM, these are independent PAM symbols. Which implies decision is similar to PAM, but remember these belong to square root M-ary PAMs, but and this is important, square root M-ary PAM. So, we are going to use the same decision rule that we have used for PAM, that is pulse amplitude modulation, but each of these belongs to a constituent square root M-ary PAM. So, the decision rule will correspond to that of a square root M-ary PAM. Okay. Now, we have already seen what the decisions are for a square root M-ary PAM. For instance, in a square root M-ary PAM, we have seen we have A 3A, correct. This is this will be, well, 2I plus 1. So, square root I equal to square root m by 2 minus 1. So, twice square root m by 2. So, this will be square root m minus 1 a minus a, so on, this will be minus square root m minus 1 times a, okay. And we already seen that the thresholds, for instance, this will remain same if it, the midpoint here is, this is 0, the midpoint here between a and 3a is 2a, and if it lies between these two thresholds, then decide a, that is if for instance R1 t less than 2a or it is greater than or equal to 0, if R1 t 0 less than or equal to R1 t less than 2a, then decide A1 equals A. Okay. So, this we have already seen this before, decide A1 equals A, and similarly we have other decision rules. And towards the end points, if for instance now you look at this, this will be square root, this point will be square root m minus, this point will be square root m minus 3a, and the midpoint here is square root m minus 2a. So, if R t is, well, if it is greater than or equal to square root m minus 2a, decide A1 equals square root m minus 1 a, because this entire decision region, there is nothing to the right of square root m minus 1, this entire decision region corresponds to A1 equals, or decide A1 or A2, in fact this is valid both for square root of m minus 1. Similarly, if it is less than square root m minus 2a, if you look at this decision region, decide A1, this is, well, decide either A1 or A2, you can generally say AI equals square root of, or minus square root of, or rather minus square root of AI. And in fact, as I was saying, you can make this very general, you do not need to restrict this to either A1 or A2, you can simply use Ri is 0 greater than equal to 0 is equal to Ri t less than 2a, then decide Ai equals a. So, if Ri t greater than equal to square root of m minus 2a, decide, well, Ai equal to square root of m minus 2a, m minus 1 is, and further I equals either 1 or 2. Okay. And similarly, you can formulate the, similarly one can formulate the rest of the cases. Remember, the decision rule corresponds to a set of cases. Similarly, one can formulate the rest of, one can formulate it for the rest of the cases, that is corresponding to minus a, right. For instance, if you look at the level minus a, you look at the midpoint on both sides. So, minus a lies between, the midpoint on the right is between minus a and a is 0, midpoint on the left between minus a and minus 3a is minus 2a. So, if it lies between the received symbol RIT lies between minus 2a to 0, then you have to decide that the transmitted symbol AI equals minus A and so on. And remember, we also call this as the nearest neighbor decision rule. That is a very powerful idea, that is basically depending on the closest constellation point you are assigning RI to RIT, basically you are assigning AI to the closest constellation point to RIT. That is the whole point. It is a very simple, if you look at it, it is very intuitive, that is you look at RIT, look at the closest constellation point in this square root M-ary PAM to RIT and choose AI as basically the closest constellation point to RIT. Okay. So, that is basically the idea. Let me just summarize this. So, choose AI equals closest constellation point in square root M-ary PAM to RIT. Okay. Choose the closest constellation point to RIT. Okay. That is the basic idea. Okay. Now, the probability of error, remember the probability of error for each PAM, let us recall probability of error first for M-ary PAM. Probability of error for M-ary PAM is, well, probability of error equals twice 1 minus 1 over m, correct, q a divided by square root n naught over square root of n naught over 2, except now we are dealing with a square root M-ary PAM. So, this is the probability of error for each individual square root M-ary PAM. Okay. So, this is the probability of error for A1 comma A2, which belong to square root M-ary, which belong to square root M-ary PAM. Okay. So, P equals twice 1 minus 1 over square root of m q a divided by square root of n naught by 2, and q is the Gaussian. I do not need to keep repeating this again. Q is the CCDF, complementary cumulative distribution function of the standard Gaussian random variable. Standard Gaussian, that is mean equal to 0. I am not repeating this explicitly, variance equal to unity, that is the tail probability, that is the tail probability of the standard Gaussian. Okay. And at this stage, I think all of you should be more than familiar with that. That is, if you look at q of x, this area is q of x, this is tail probability of standard Gaussian. Tail probability of the standard Gaussian random variable, and further for M-ary QAM we have derived it as A as given symbol. Remember, we said given symbol energy, yes, each individual square root M-ary PAM has each individual square root M-ary PAM has average energy Es by 2, which means, and for that we have derived the condition, the corresponding condition is amplitude A equals square root 3 ES by 2m minus 1. This ensures average symbol energy ES by 2, okay, or ensures average energy ES for the entire PAM, average energy ES by 2. So, this ensures, this value of A ensures average symbol energy ES by 2 for each square root M-ary PAM, and average energy ES, because average energy ES by 2 for each square root M-ary PAM, the total average energy will be the sum of the component average energies, that is ES for the overall M-ary QAM. So, the only thing left now is to substitute this value of A. So, PE, we have a beautiful result, PE is twice 1 minus 1 over square root of M Q, substitute the value of A, which is 3 ES by 2m minus 1 into n naught by 2, which is equal to, so PE 2 1 minus square root of m q square root of, well, 3 ES by n naught into m minus 1. Okay. So, this is the average energy for each constituent, average probability, I am sorry, average probability of error or average symbol error rate for each constituent average symbol energy for each constituent square root M-ary PAM, and similar to QPSK, again similar to QPSK. Now, this is the average energy, average symbol error rate for each constituent square root M-ary PAM. Now, the overall QAM symbol will be in error if either of the PAM symbols is in error. Okay. And therefore, similar to QPSK, right, the overall symbol is in error if either of the component bits are in error. Alright. So, overall QAM is in error if either of the constituent PAM symbols are in error. Therefore, the overall error rate for the overall M-ary QAM constellation can be derived as is, well, PE equals, let us write this as PE QAM, that is 1 minus, remember we derived this, again I am not going through the entire derivation, 1 minus the constituent PAM error rate, which is 1 minus 1 plus PE PAM square minus twice PE PAM, which is equal to, well, twice PE PAM minus PE PAM whole square, which is approximately equal to twice the error rate of the constituent PAM, because at high SNR PE PAM square, this is a square is very small, because this square term at high SNR, this is very small, in comparison to P palm square is very small in comparison to P palm. So, the error rate finally, overall error rate for the QAM, for the M-ary QAM is equal to twice, dropping the approximation for simplicity, twice 1 minus 1 over, or let me just write it, twice 1 minus 1 over, I have dropped the approximation sign, q square root of 3 ES by n naught m minus. Okay, so this is twice. Let me just write it a little bit more clearly. This is twice 1 minus 1 over square root of m q three ES by n naught into m minus 1. Okay. So, this is the error rate for the overall QAM. Now, before we wrap this up, let us look at a simple constellation diagram for the M-ary QAM. For M-ary QAM, let us consider a simple case where m equal to 16, which means each constituent square root of 4 PAM. So, A1 comma A2 belong to a square root of 4 square root of 16, that is 4 PAM. So, basically A1 belongs to the set of 4 levels minus 3A, minus A comma 3A, A2 also belongs to minus 3A, minus A comma 3A. So, these are the levels corresponding to levels of the 4 PAM or the square root of 16 PAM. Okay. And these can be, so I can represent A1 on the x axis, A2 or the levels of A1 on the x axis. So, here I have A minus A, 3A minus 3A. Similarly, on the y axis I have the levels of A2, A, 3A minus A minus 3A, and this is A. So, this corresponds to the point AA, this corresponds to the point minus AA, similarly 3A comma A. So, this will have a total of course, we are considering m equal to 16. So, naturally, this will have a total of 16 points in the constellation. Okay. For instance, if you look at this point corresponds to A1 equals 3A, A2 equals minus A. Remember, this corresponds to A1, y axis corresponds to A2. So, there are total of 16 points . naturally this is 16 QAM constellation. So, there are a total of 16 points in the 16 QAM. Observe A1 belongs to a linear PAM, that is a PAM on a line. Remember, PAM is a linear constellation, that is it can be represented on a line. Okay. So, here we have a QAM, all right, which has a constituent square root M-ary PAM A1 on a line, that is x axis, another constituent square root M-ary PAM A2 on the line, which is y axis. Therefore, if you look at the net constellation, this looks like a square, all right. So, this is also known as a square constellation. So, a QAM is a square constellation. Okay. So, this is a very interesting observation. So, you can see that the QAM is a square QAM is a square constellation. There is a symmetry. Okay. So, it is a QAM is a square constellation, and of course, we have seen the number of bits equals log 2 to the base m, m equal to 16. If m is equal to 16, number of bits equals log 16 to the base 2 equal to 4 bits, 2 bits on each, of course 2 bits on each constituent PAM. Bits on each constituent PAM, and further, as I have said in the beginning of this module, that QAM is a very general constellation, it is a very powerful constellation, alright, because you can transmit individual PAM symbols on both the in phase and quadrature pulses, correct, in phase and quadrature components, and it can scale, right. With m equal to 16 you get 4 bits, with m equal to 64 you get 6 bits per symbol, m equal to 256 you get 8 bits per symbol, 512, 1024 and so on. Okay. So, there are all several different possibilities. So, you have m equal to, of course, if m is equal to 4, that is QPSK, 16 QAM, 64 QAM, 256 QAM, 1024 and so on. So, these are all the QAM. So, this is of course your 4 symbols, means 2 bits, means 1 bit on each in phase and quadrature. This is of course your QPSK. Okay. And number of bits equals 2, 4, that is log to the base 2 of this quantity, 2, 4, 6, 8, 10, of course you can add 2048, 4096 and you will have 12 bits. So, the number of bits increases. Okay. So, therefore, by choosing an intelligent QAM modulation to suit the channel requirements, one can scale the bits. You can go from 2 bits to 4 bits to 6 bits to. So, and remember, when you are increasing the number of bits per symbol for the same symbol rate, let us say you have a symbol rate of 1000 symbols per second or 1 mega symbol per second. If you choose QPSK, which has 2 bits per symbol, you get 2 megabit per second. If you choose 1024 QAM, which has 10 bits per symbol, right, you get 10 megabit per second. Alright. So, by choosing a suitable QAM, one can scale up the data rate, and that is how high data rate is achieved, right. High data rate is achieved in for instance 3G, 4G and 5G, and also in the future 5G cellular networks, by scaling up the modulation. Okay. This is known as higher order QAM or higher order modulation. Okay. So, these basically this is known as the higher order. For instance, when you go from QPSK to all these, this is known as and modulation can be chosen adaptively, correct. Modulation can be chosen adaptively. to meet rate requirements. Okay. And this is termed as adaptive modulation, which is yet another important scheme. So, higher order modulation and adaptive modulation. Higher order modulation plus these are important in to achieve higher data rates in 3G, 4G and also 5G. In 3G, 4G and 5G. So, when the rates go from hundreds of kilobit per second to megabit per second to tens of megabit per second to in fact a gigabit per second, right. These can be achieved, of course, achieved by several technologies, several components. I am not saying that higher order modulation is the only technology component in achieving higher data rates, but higher order modulation, usage of higher order modulation is one of the strategies, one of the main strategies that can be employed to multiply the bit rate several times. That is for the same symbol rate, right, for the same symbol rate. For instance, if you have a symbol rate of 10 mega symbols per second, if you use 4 QAM, that is QPSK, which has 2 bits per symbol, you get a data rate of 20 bits or 20 megabits per second, 20 Mbps. And if you can succeed in using 1024 QAM, which has 10 bits per symbol, you can get a data rate of 100 Mbps. So, you can see from 20 Mbps to 100 Mbps, that is a factor of 5, that is a factor of 5 into 5. So, that is a factor of 5 in data rate. Okay. So, you can go from, so let us say this can be a 3G data rate, this can be a 4G data rate. So, 3G systems typically have data rates around Mbps or at most 10 Mbps. In 4G you can go up to data rates of 100 Mbps and in fact more, you can go to data rates of about 200 to 300 Mbps. Okay. So, it all depends on the modulation scheme used, along of course along with several other technologies, but modulation, right, and adaptively choosing the modulation depending on the user and user requirements. So, the modulation scheme depends on one, the requirement of the user, right, what kind of the rate the user requires, and also the channel condition, if the wireless channel is able to support such a data rate. So, adaptively one can modulate, one can choose an appropriate modulation, right, to meet the data rate requirements and of course deliver the maximum data rate to each user. Okay. So, that increases the data rate significantly as we go from 3G to 4G to 5G wireless technologies, and QAM is a very general and is one of the most widely used modulation schemes. So, let me just summarize that QAM is one of the most simplest, powerful, and it is one of the most widely used it is one of the most widely used, it is very flexible, one of the most widely used modulation schemes. alright. So, in this module we have comprehensively covered QAM, that is what is the constellation, what is the structure of the, what is the structure of QAM, what is the structure of the transmitted waveform, what is the processing at the receiver, and the associated probability, the probability of error for M-ary QAM, and also the importance of this QAM with respect to the modern wireless technologies, alright. So, we will stop here and continue with other aspects in subsequent modules. Thank you very much.